Hey everyone, welcome back to the Pi Files. I am Moti Mummudi. In episode 1, we talked about why traditional scale-up rules are broken. Today, in episode 2, we're applying that directly to biomanufacturing. We're tackling the ultimate biological tightrope, the Shear-Oxygen paradox. How do we keep our fragile living cells breathing without accidentally tearing them apart? Let's dive in. Scaling up mammalian cell cultures like CHO cells for monoclonal antibodies is a massive balancing act. Unlike simple chemical reactions or bacteria, these cells lack a rigid cell wall. They're incredibly fragile. When you move from a perfectly mixed 2-liter benchtop flask to a massive 20,000-liter commercial vessel, the physical extremes of the fluid are totally magnified. And because of this, just delivering basic oxygen becomes a life or death engineering challenge. Let's look at the first side of this problem, starvation. To keep cells alive, you have to sparge gas and agitate the tank to drive your volumetric mass transfer, or KLA. If your agitation is too slow or too low, you get stagnant dead zones at the top or bottom of the tank. When cells enter these zones, they experience hypoxia. They panic, alter their metabolism, and trigger toxic lactate spikes. The result? Your batch is poisoned and your product yield is destroyed. So the obvious fix is just to spin the impeller faster to mix it up, right? Wrong. When you crank up the agitation, you introduce the danger of destructive shear, which we measure as the energy dissipation rate, or EDR. The tips of your impeller blades become violent, high-velocity hotspots. When those fragile cells pass through these zones, the mechanical force literally shreds them. This causes catastrophic cell lysis. So this right here is a Shear-Oxygen tightrope. On the left-hand side of this graph, if your agitation is too low, you fall into the lactate or starvation zone. On the right-hand side, if you mix too hard, you fall into the cell death and lysis zone. At the commercial scale, your survival margin in the middle is razor thin. You have to mix aggressively enough to deliver oxygen, but gently enough to keep your cells intact. For decades, engineers tried to walk this tightrope using averages like power per volume or P over V. This is a fatal trap though. Look at the visual on the left. That gray cylinder is a mathematical illusion of an average. Now look at the right. That is a chaotic biological reality. Averages mask physical extremes. A cell doesn't care what the average energy of a 20,000-liter tank is. It only cares about the localized trauma it experiences when it hits the blade. Scaling by averages guarantees scale-up failure. So how do we fix it? We map the extremes using process metrics-driven hybrid modeling. We take the rigorous localized fluid dynamics of CFD and we fuse it with the algorithmic speed of machine learning. Now, this creates what we call a digital nameplate for your specific vessel. Instead of useless averages, we digitally map the exact 3D distributions of shear and oxygen throughout the entire tank. And here is the payoff. By mapping these distributions, we can run virtual experiments to find the exact operational sweet spot. We can pinpoint the perfect sparging and RPM parameters that guarantee KLA while strictly capping your EDR. We're replacing guesswork with predictive modeling, saving millions of dollars, and ensuring that your high-stakes PPQ campaigns are a total success. Stop wrangling spreadsheets and let's start engineering smarter. And before you go, make sure you hit the subscribe button so you don't miss episode 3. We're going to shift gears from biologics to small molecule manufacturing, diving into fast chemistry, zombie impurities, and exactly what happens when your reaction is actually faster than your mixing time. You won't want to miss it. I'll see you then.